Now I'm going to go ahead and start letting folks in from the waiting room. Hi, everyone. Welcome. We'll get started in just a few moments. We're letting folks in join from the waiting room. Hi, folks. Welcome. We're going to get started in just a minute so folks can join in from the waiting room. We appreciate you all taking your Wednesday with us. All right. It looks like everybody has joined. So, hi, friends. Welcome to SECOORA's webinar, Preparing for Hurricane Season, Observing Systems, Data, and Tools. My name is Abby Wakely, SECOORA's Director of Communications, and I will be facilitating and moderating the webinar. We're very, very excited to host this webinar to show how our observing system, data, and tools can support hurricane forecasting and informed decision-making. During the webinar, we highly encourage you to ask questions at any time for the presenters or technical questions for me by typing them in the chat box. I will pose the questions to the presenters after their presentation during our Q&A time. We are recording the webinar today and will be posting the recording on our website. We are very excited and lucky to welcome 4 speakers. We have Debra Hernandez from SECOORA, Greg Dusek from Dusek Coastal Science and Consulting, Lynn Leonard from University of North Carolina, Wilmington, and Catherine Edwards from University of Georgia, Skidaway Institute of Oceanography. Debra is our first speaker today, and Debra is the executive director of SECOORA. Since joining SECOORA, she has been the lead PI on several multi-year regional observing projects and has served on related marine policy and science programs. Her experience includes coastal and ocean engineering, management, and policy. Debra, you're up first. Take it away.
Great. Thanks so much, Abby. I'd like to take just a moment and recognize you for organizing us all today and to add my thanks for our panelists as well as to all of you for spending time with us here today. So I'll be providing a brief overview of SECOORA, which stands for the Southeast Coastal Ocean Observing Regional Association. Next slide. SECOORA is committed to serving communities throughout the Southeast. Our vision for the region is thriving coast powered by easily accessible and trusted data. We'll achieve that vision by empowering people and communities with reliable coastal and ocean data. As we saw with Hurricane Helene back in September of 2024, even the most inland communities in our region can be severely damaged by hurricanes, meaning that data and information that we are able to make available with funding from NOAA and in partnership with some of the experts you'll hear from today, it is vitally important throughout the region. Next slide. SECOORA has the privilege of working with technical and scientific experts to collect a broad range of data types from sensors deployed throughout the region. This graphic provides a high-level overview of our network and the observing assets that are funded by our program and where they're located. What's unique about our network is we're the only federally certified observing system for our region. All the data and information from the sensors are transmitted to SECOORA data servers, quality controlled to federal standards, and provided through robust data pipelines to NOAA and other federal environmental data centers. That means the data is available to weather and hurricane forecasters in near real time, as well as freely available to the public, port operators, emergency managers, and a host of other people and communities that can be impacted by coastal weather and storms. Before we continue, I'd like to take a quick moment to acknowledge the major challenge that one of our key observing operators is currently facing. The losses at the Marine Science Building at the University of South Florida to fire are deeply felt by our community. On behalf of the entire SECOORA team, we extend our support and best wishes to everyone impacted as recovery efforts move forward. Next slide. I'd also like to acknowledge the NOAA National Hurricane Center and all the local National Weather Service offices throughout the region. They are the experts when it comes to notification of impending impacts from storms. SECOORA has a supporting role by helping to make weather forecasts better. We work in 4 areas during hurricanes. We provide data to inform and verify forecasts. We quality control the data and make it freely available. We communicate about storms, amplifying the work of NOAA and other key emergency managers, and we provide educational information and opportunities to help make communities more prepared. Next slide. Before hurricane season, we make sure our resource hub is updated and current. We consolidate trusted resources in one place. We provide access to data from the broad array of sensors, which I've mentioned already. We utilize trusted sources like NOAA, other integrated ocean observing system regional associations, other federal agencies, and academic experts. Once a storm forms, we use our communication channels to amplify the messages from NOAA and others about the storm. This supports a unified cross-regional approach to preparedness and awareness. Once it's clear that a storm's likely to impact the Southeast, we create a storm-specific web page to make access to the most relevant information even more clearly and centrally located and available. Next slide. During the storm, we provide real-time information when it matters the most. As seen in this quote from National Weather Service, our near real-time data from the network of buoys, cameras, and water level stations gives weather forecasters a way to ground truth their predictions and provide the best information possible to warn the public. Our Eyes on the Storm data product aggregates and creates graphics of data from any sensor within 50 miles of the storm. It is publicly available and allows anyone to explore real-time conditions and better understand what's happening as the storm unfolds. So this is for the weather nerds that might be on the call here. Next slide. Post-storm, SECOORA works with our sensor operators to assess damage to the observing systems and report that information to NOAA and Congress so they understand the need for repairs to the network, which is essentially critical infrastructure for hurricane preparedness and prediction. We also continue to share real-time data from cameras, water level stations, and other sensors so that communities and the impacted public have access to information that can inform decisions about returning home as well as recovery efforts. So thank you very much for your attention. Hopefully I've provided some insight into SECOORA operations as they relate to hurricane preparedness and response. I'm going to hand things back to Abby and look forward to the panel presentations and discussion with all of you at their conclusion.
Great. Thanks so much, Deborah. And as a reminder, you can ask questions at any time and we will pose them to the presenters at the Q&A session. So I'm going to go ahead and stop sharing my screen and pass it on to our next speaker, Dr. Greg Dusek. Dr. Greg Dusek is a physical oceanographer and principal at Dusek Coastal Science and Consulting. He also serves as co-executive director of the U.S. Coastal Research Program and is adjunct associate professor at North Carolina State University. His research focuses on advancing coastal hazard monitoring and prediction through data-driven methods. And I can see your screen, Greg, so thank you so much. Take it away. And you are muted, if you can unmute yourself.
You'd think by now I'd have this figured out. All right, thank you, Abby, and thank you, Abby and Deborah, for inviting me to this event, and really awesome to be part of this panel with Lynn and Catherine as well. Just a great group to talk about this with you. And so I'm going to be talking about two data sets, webcams and water levels. These are things that, I spent over 14 years with NOAA, and part of that time I worked closely with SECOORA on both of these projects. And so wanted to just walk you through how these data might help you as you prepare for this upcoming hurricane season and beyond. So in terms of the context here, how can we use these data? So looking back and to 2023 and Hurricane Idalia, which you might remember, made landfall along the Big Bend of Florida on August 30th as a Category 3 storm. And it led to significant amounts of damage and flooding, flooding in the Tampa region, damage throughout the Florida Gulf Coast. And estimated damages exceeded $3.6 billion. And there were 12 lives lost. But the extent of the impact wasn't limited to just the Florida coast. The storm made landfall and then went off the coast in South Carolina. And you can see from the map here, there was an expectation of potential storm surge along the Georgia and South Carolina coasts, and even into North Carolina. And what we saw is that in Charleston, there was significant coastal flooding. And NOAA has a water level gauge in Charleston, and the WebCOOS team decided to work with the NOAA team to put a webcam on that gauge, co-located, to be able to assess impacts for events like this. And so this is a view from the cam and the water level data from the NOAA sensor on the bottom there. And this is in meters relative to mean high water, the daily average high tide. And so at low tide of that day, you can see what the conditions are like. And as I play this video, you can see tide is rising, Idalia is approaching, and water levels start to rise. And we go over that mean high water threshold and hit the minor flood threshold, which is when we expect to see minor flooding in the region. You could see water starting to spill over onto the walkways there and then the nearby roads. And then as we continue the video here, going up to past major flooding and up to peak surge, you can see that the area is completely inundated. It turns out that the peak of this event was 1.056 meters, or over 3 feet above mean high water, which is the sixth highest observed water level at this site since it was started recording in 1921. So over 100 years of water level data, this is the sixth highest. And I think this gives you an idea of what impacts associated with that water level are. And so that's one of the values of co-locating these sensors together. You don't just have a number associated with a flood event, but you can start understanding associated impacts. And then shout out to one of my colleagues, Matt Conlon, for helping me put together this Enlon WebCOOS synchronizer. So if you go to that QR code, you could generate these for any WebCOOS and Enlon camera for any time period of interest. So a cool little tool there. So I'm going to quickly talk about a little bit about water levels. You can see a water level sensor there on the right and webcams on the left. I'll start with water levels. And Debra introduced this already, but SECOORA has really been a leader in community water level monitoring. They started the Southeast Water Level Network. And the goal here was really partnering with communities to monitor flood risk and improve resilience. And one of the things, being at NOAA for so long, working in the Tides and Currents office, where we have over 300 water level sensors across the US, I see the value for this data, but we can't have them everywhere, right? 300 stations across the US, 90,000 miles of coastline. There's obviously gaps in terms of where we can observe water levels. And that's really where these type of data step in, to be able to fill those gaps and provide complementary data to help communities prepare for flood risk, which is only getting worse, and make decisions. And so this network's really been a partnership effort. You can see the different partners involved there. And credit to Jen and Cody for leading this and really moving it forward rapidly. In terms of accessing the data, you can go to wl.secoora.org and view the map and check any of these sensors out. And you click on them, you can get a real-time view, check it relative to predictions, look at historic data, and even look at the data relative to a threshold, and then get notified if the water levels exceed that threshold. And then, of course, if you're more data savvy, you can use OpenDAP and ERDAP to access these data as well. In terms of the value beyond just monitoring conditions as they occur, one of the things you can also do with these data is look at past storms. And so here's an example from Hohonu. This is in the Lee County region on the Florida Gulf Coast. Hohonu is one of the partners with SECOORA, so a number of these are SECOORA stations, and I've had the privilege of working with the Hohonu team over the last few months. But I think this is a great example of looking at Hurricane Helene and Hurricane Milton, how you can see impacts spatially and not just at a single point in the region. So assess where, what are the surge levels across a region, and then combining these data with onshore overland flood sensors, you can start associating those water levels with flood impacts on the ground. So I think a good example of how to use these data in kind of a retrospective approach. And then I also want to mention the NOAA Coastal Inundation Dashboard. And so, when you have a storm actively occurring, you can go here, you can use the QR code there to view it. And you'll see active tropical systems on the map, their track, as well as the watches and warnings associated with those, and flood watches and warnings. And you can see there was a flood warning for when I took this screenshot. But critically important here is that SECOORA is the first RA to have their water level data in the Coastal Inundation Dashboard. So you can see those red dots. Those are SECOORA stations. And so you can go here and see all at once a number of the SECOORA stations, the NOAA stations, and really assess what water levels look like across a region in real time. And then not only that, but they have links to the WebCOOS web cameras here. You can see those little green dots. So you can go here and then get to your nearest webcam to look at the shot like I showed you with Charleston. And so that brings me to my next topic, the WebCOOS web camera network. And WebCOOS is the Webcam Coastal Ocean, the Coastal Observing System. This started back in 2017 as WebCAT, the Webcam Coastal Application Testbed. And then over the last few years, we launched it into an operational network in the Southeast, and then further extended it into a national operational network. And being led by SECOORA, and great work by Theo and the team there in terms of spinning this up, and now expanding to 67 total cameras, which is incredible. 52 of them are active, and there's another 30 or so planned. And as Debra mentioned, about 23 of those active cameras are in the Southeast. And the goal with this was really about, providing additional imagery observations that can be used for real-time monitoring, decision-making, and science, and answering science and research questions. It's been a partnership with NOAA's been involved with this, academic partners, private sector partners. Axiom that handles the data, Surfline is doing camera installs. And if you want to check out the data, you can check out webcoos.org. Or if you're data savvy, we have a Python WebCOOS client, so you can access the API and bring in any of the imagery you want into your workflow. In terms of how these data help during hurricane season, during and after storms, there's a few things. One is rip current detection. So, when there's a storm, especially offshore, and there might not be direct flood impacts, but there can be large waves, and large waves drive rip currents. And we see a lot of drownings, like in Idalia, where 8 of those fatalities were actually surf zone drownings. And so this is showing you a rip current detection approach that was done by our partners at UC Santa Cruz. On the left there, you can see an example of the approach when we were developing it. On the right is an operational rip current detection in the Holland Beach camera. And this is running experimentally right now at a number of the WebCOOS sites. Another use case, and Debra mentioned this, is situational monitoring. And in particular, looking at beach use and what are the situations on the beach during hazardous events, leading up to and during and after. And so this is Hampton Inn in Corolla, North Carolina, there on the left, and Corova Beach in the Northern Outer Banks on the right. And you can see showing counting people and vehicles, boats, et cetera. And so these are operational also on the WebCOOS website right now. And so we give you an insight into, what are the beach use? Are there people on the beach? Are there potential, do we have to send people out there maybe from a public safety standpoint, et cetera? So a nice use case there. And that was led by University of South Carolina, Jeremy Cothran and Dwayne Porter. In addition, there's also wave impacts when you have large storms. So on the left there is actually a view at the Oak Island camera in WebCOOS during Idalia, and you could see large waves impacting the dune line there during the storm. So at times like that, you're going to potentially lead to coastal erosion and overwash. And so having the cameras enable you to monitor that in real time, and then also help look backward and validate models like the USGS has to monitoring total water levels during storm events. And then on the right, work by Joe Long and his team at UNC Wilmington to use the data to track shoreline change over time and look at how like nourishment and erosion affects beach width, and be able to assess potential dune and infrastructure impacts. And then I mentioned flood monitoring already, but I wanted to cite another use case. So this is flood monitoring in more urban and suburban areas. This is using cameras to monitor, in some cases, rain-driven flooding. So this is during Hurricane Ian near Charleston. On the left there, the water is not a lake. That's supposed to be kind of a grassy area there in the neighborhood. And so they see frequent flood events during high rain events. And so the cameras were installed there to be able to document those. When was flooding occurring? What were the conditions leading up to that? And we have a number of these kind of more inland cameras, and these were led by University of South Carolina and Jeremy Cothran and Dwayne Porter. And then lastly, I just want to finish up with Surfline. Again, one of the WebCOOS partners. They're doing some really innovative stuff with web camera imagery using AI. And so if I play this video, you can see the detection of the land-water interface, wave run-up, wave heights, people on the beach, and segmenting the different components of the image. And so this AI tech is really cutting edge, quite impressive. And when you think about storm impacts, it can help assess wave impacts in real time. And they have some work that enables them to measure beach profiles from the imagery. So you could actually assess, how much erosion is happening during and after storms without having to necessarily go out and survey the coast. So that's it for me. Thank you. And I'll pass it back to Abby.
Great. Thanks so much, Greg. I really appreciate your presentation and how you visualize the co-location of the water level sensors and the web camera. It's so important for communities to really understand what that data means. And so next up we have Dr. Lynn Leonard. Lynn, you can go ahead and share your screen. Dr. Leonard currently serves as the Associate Director for Research and Innovation at the University of North Carolina, Wilmington Center for Marine Science. She is a marine scientist who specializes in coastal hydrology, marine geology, and ocean observation. She is also director of the Coastal Ocean Research and Monitoring Program, CORMP, housed at UNCW Center for Marine Science, which she'll talk about today. Lynn, go ahead and take it away.
Great, Abby, can you see everything okay on your end?
I sure can. Thanks.
All right. Well, before I get started, I also want to thank Abby and Debra for the opportunity to participate in today's webinar, and also everybody else who's out there in the audience and interested in learning more about SECOORA. So for my presentation, we're going to be moving out over the ocean, and I'll be talking about instrumented ocean buoys and what these systems can tell us about hurricanes and how the data are used before, during, and after storms. So as Debra mentioned earlier, the instrumented ocean buoys are a core component of the SECOORA observing system, and SECOORA supports or hosts observations provided by almost 40 moored buoy platforms in the coastal waters of the southeastern U.S. On the map here, I just kind of want to highlight the stations that are operated by SECOORA member institutions in this bluish purple color, as well as platforms that are operated by our affiliated partners, which are shown in green. Importantly, the SECOORA supported buoys help fill critical observational gaps in coastal waters where data are often limited, but where localized ground truth measurements are needed for situational awareness and for improving coastal warnings as storms make landfall. So just to give you an overview here, we're looking at examples of different types of buoys that are located within the SECOORA observing domain. These systems are eyes on the water, providing real-time, quality-assured meteorological water wave condition information that helps us better understand and predict storm behavior. Now, a buoy is not a buoy. And so while some buoys are specialized, this is an example of a wave buoy here on the right, also a different type of buoy over here in the bottom left-hand corner. Others measure and report a range of variables from both above and below the water surface. And these are just examples of some of the parameters that you might see reported by buoys through the SECOORA data portal. All of the data are reported at least once per hour, if not more frequently, and they are available 24/7 year-round through SECOORA, as Debra mentioned earlier, or through some of the partner data portals. So because these platforms are already in place and operational, a buoy that is within a potential storm path is already transmitting real-time conditions at or near the ocean surface, even before a storm develops, often shedding light on the conditions conducive to storm formation. And some of the stations operated by SECOORA, including several that are operated by our colleagues at the University of South Florida's COMPS program, also provide subsurface data. And in the example shown here, I just wanted to highlight the real-time water temperature data that's collected and reported at multiple depths beneath the surface. In terms of hurricanes, this information is important because it can be used to estimate ocean heat content, which is the energy that can fuel rapid storm intensification, such as we saw in 2022 when Hurricane Ian rapidly intensified from a Category 3 storm to a Cat 5 storm as it transited the West Florida shelf. Now, as we've heard earlier, all of these real-time or near real-time data are accessible to any interested user, but they are particularly valuable to National Weather Service forecasters during tropical cyclone events, which is the topic of today's webinar. So one of the primary uses of buoy data during tropical cyclone operations is forecast validation, especially for winds. And as a storm approaches, and I'm going to be referring a lot to Hurricane Aaron last August, and as we see here, the real-time data are reported, and the forecasters can use these observations to help define the extent of tropical storm force winds and also to improve estimates of arrival time and impact potential, information that directly supports emergency managers as well as community preparedness. The buoys also inform surface level wind validations. So by measuring winds close to the ocean surface, the buoy data can help confirm whether aircraft reported winds, such as those reported from like the hurricane hunters, are accurately translated to conditions that exist at the surface. And so while wind is certainly a key part of the forecast, it's only one piece of the story. Buoys also provide critical insight into ocean conditions and especially waves. And Greg mentioned a little bit about that a second ago, which can pose significant hazards even before a storm arrives. So spectral wave data, which basically conveys the distribution of wave energy over different directions and frequencies, and this is sort of what it would look like, is derived from buoy data or actually reported in some cases by wave buoys. And this information allows forecasters to identify conditions that increase the likelihood of dangerous rip currents as Greg mentioned in the previous presentation. And this then allows our National Weather Service partners to issue public alerts, such as you see here, several days ahead of a storm. The real-time data also help marine forecasters detect the development of steep waves, and these are potentially dangerous waves, especially near inlets where navigation risks can increase well before a storm nears the coast. Additionally, the buoy observations feed directly into coastal water forecasts issued by the National Weather Service Forecast Office. And these are reports that predict the nearshore weather and sea state conditions and are used by mariners to make go, no-go decisions and to also help inform the public about risks like the coastal flooding, like we just heard about in the previous presentation. So as a storm starts to move closer to landfall, the buoy data are also routinely incorporated into National Weather Service public advisories, and I just grabbed a few examples here that talk about the buoy data, and also included in briefings for core Weather Service partners, and these would include emergency management groups and the U.S. Coast Guard. These briefings highlight the evolving upstream storm conditions, which help to guide the execution of hurricane preparedness plans and support operational decisions that are intended to protect people and property. So beyond operational uses, buoys occasionally provide something rare and invaluable. They give us a front row seat to the storm's core while while the eye is just offshore. So today I just want to briefly highlight two examples. The first is Hurricane Isaias, which in August of 22 passed directly over a buoy located off of Sunset Beach, North Carolina. This time series shows the pressure data in black, peak sustained winds in blue, and we see the classic signature of a storm passage, a sharp drop in pressure paired with increased winds in the eye wall. Here, the peak sustained winds reached about 50 miles per hour, followed by a brief lull as the eye moved overhead, and then the winds quickly increased again as the backside of the storm moved over the buoy and the storm made landfall. A second example is Tropical Storm Idalia in August of 2023. After making landfall in Florida, as we previously heard, and re-emerging into the Atlantic off the South Carolina coast, the storm center passed very close to a buoy near Capers Island, South Carolina, that captured wind pressure and wave data. In this example, we see another clear record of near storm center passage, maximum winds and waves before the eye, a pronounced pressure drop and decrease in wind with eye passage, followed by a slight rebound in the winds and decreasing wave heights as the storm moved away from the coast and further offshore. Now, after the storm, the buoy data continue to remain an essential resource. The observations are included in National Weather Service and Hurricane Center post-storm reports, as highlighted here for this report for Tropical Storm Idalia. And they're used to establish detailed accounts of storm impacts for Hurricane Center and National Weather Service reports. The data contribute to emergency management after action reporting. They support meteorological analysis and research, and they also add to long-term climate records. Moreover, by enabling comparisons of measured conditions to model predictions, the buoy data also support post-storm forecast verifications. And this allows researchers to identify areas of improvement and enhance predictive capabilities. And so, for instance, in a scene in this example for Hurricane Erin, the Coastal Data Information Program out of Scripps uses wave observations from offshore buoys, which here we see some examples of observations in blue, to evaluate model performance, shown by these red and yellow lines in these panels, to identify discrepancies between observations and model output, and then to use this information to inform updates to the models that are used to drive the wave forecasts, especially for high-risk events like hurricanes. So in all of these ways, the buoy data continue to add value long after a storm is over. And so with that, I'll conclude my part of today's presentation. To learn more about SECOORA's buoy network or to access real-time data, please visit the SECOORA website. And I'm not going to call them, Debra, I'm not going to call them storm nerds. I'm going to call them storm enthusiasts. But for those of you that are out there in the audience, I do encourage you to explore SECOORA's Eyes on the Storm portal, in addition to the other resources that you'll learn about today. And I thank you for your time, and I'll be around for the Q&A. Thank you.
Great. Thanks so much, Lynn. Really appreciate you highlighting how the real-time data from buoys is used by many emergency management partners, from detecting waves to ground truthing their model observations and forecasting. All right, on to our last speaker, Dr. Catherine Edwards. You can go ahead and start sharing your screen. Dr. Edwards is a physical oceanographer and associate professor at Skidaway Institute of Oceanography and in the Department of Marine Sciences at University of Georgia, where she is also a fellow in the Institute for Artificial Intelligence and adjunct faculty in College of Engineering. Catherine's research focuses on answering fundamental questions in coastal oceanography and fishery sciences with autonomous underwater vehicles, developing novel ways to optimize their use with engineering principles and real-time data streams from models and observations. Catherine, take it away, and I can see your screen.
Great. Thanks so much for the kind introduction. I get to talk today about how we use autonomous underwater vehicles to improve tropical storm intensity forecasts. This is a project I lead as the lead of the SECOORA Regional Glider Observatory with my co-PIs Chad Lemke at USF and Harvey Syme at the University of North Carolina at Chapel Hill. But really, this is a much larger project. This is our regional part of a national and even international project to use autonomous systems to improve forecasts of tropical storms. This is through Navy, NOAA, and academic partners. So I'll first get into the intensity problem and then talk about the contributions we've made through SECOORA. And then as many as time allows, I'll get into some highlights from the last several years and kind of future plans. So in terms of errors in forecasting, we can think of errors in forecasting in two different categories. One is in the forecast error in terms of where the storm is going to go. And this is an image showing from the National Hurricane Center showing the forecast error over the last 55 years, showing that over time, our forecasts are getting better. Our error in terms of where the storm is going has gotten much, 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 much smaller. And we're able to provide reliable products in terms of track error further out. So not just a reliable 24 or 48 hour, but we're starting to get more reliable 5-day forecasts and even longer. So this is all super encouraging. But the other way we think about forecast errors is in terms of its intensity. Now that we know where it's going, how strong is it going to be? Let's think about the path error for a second. Here is a cone of uncertainty. Those of us who have lived in the cone know its meaning, but it shows the likely passage of the center of the storm over the upcoming forecast. And Hurricane Dorian is a really useful storm to consider how these changes in improvements in track forecasting, what they mean for people who live in the cone. So this is from Hurricane Dorian in 2019. If you use the cone from 1990, this is how much uncertainty you might have in terms of where the storm might be headed. And if you go back to the 1970 cone, you lose the ability to see even what basin the storm may go into. So these improvements in track forecast error have been really significant and have continued to improve. Now, in terms of hurricane intensity, these improvements have come more slowly. So this shows the forecast error in knots for the 24-hour, 48, 72-hour, and then for the longer range forecasts since 1990. And I want to point out that the slopes of these errors, so there is improvement in hurricane intensity error, but it is coming much more slowly than we see in track error. And the other thing I want to point out is that these magnitudes of forecast error are on the order of 10 to 15 knots. And that's potentially 1 to 2 categories on the Saffir-Simpson scale. So why is this happening? There's been some focus, and already in Dr. Leonard's presentation, she mentioned the idea of rapid intensification. It's this idea that a storm can gain huge amounts of strength over short periods. It's the nightmare scenario. You go to bed, and a hurricane's a Category 1. You wake up, and it's a Category 3 or 4. So we define rapid intensification as a change of 30 knots in wind speed in 24 hours or less. So if you take those statistics from all of the storms in the prior slide and consider only the cases when rapid intensification was observed or forecast, you see that the forecast errors are very, very large. These are errors on the order of 20 to 30 knots. And there's a lot of variability where some of these forecast errors, and these are average over the Atlantic and Pacific basins, can be very, very large and may be driving, especially some of these larger errors. These 20 to 30 knot differences are potentially 2 to 3 categories on the Saffir-Simpson scale. Now, the Saffir-Simpson scale is not perfect, but colloquially, we all have ideas. I'll stay for a 3, I'll leave for a 4. And these are the numbers in the forecast products that are used by emergency managers and decision makers to guide evacuations of different zones and stuff. So perfect or not, these numbers have meaning, and tropical storm intensity and rapid intensification cause problems for people trying to get to safety, for decision makers trying to protect their communities. And when these errors, it's not just a rapid intensification, this can happen in the opposite direction too, when a storm loses strength as it comes close to the coast, and it is forecast to be stronger than it actually appears, that can erode public trust. So getting these forecast errors, the intensity errors improved is a major priority. So what fuels rapid intensification? And ocean heat is a major contributor to this rapid intensification of storms. So we can define in terms of ocean heat as an integrated heat greater than 26 degrees Celsius. And the right-hand side shows the amount of water, not just at the surface, but integrated all the way down to 26 degrees Celsius as the heats that's potentially available to mix and potentially fuel hurricane intensity. And NOAA is intently looking at these, making maps and operational products that map where this tropical cyclone heat potential is strongest. And you see these areas of strong heat exist in the Caribbean, the Gulf of Mexico, and in the SECOORA footprint as well. So this is really one of the main motivations for gliders, which are autonomous underwater vehicles that fly up and down in the water column, collecting measurements of temperature and salinity from the surface all the way to the bottom. They come up to the surface and report a subset of their data. So we're getting near real-time information of what this tropical cyclone heat potential is and what its distribution is in space with these vehicles. So this idea gave birth to the idea of the national and now international Hurricane Gliders Project, with the goal of deploying gliders into so-called essential ocean features that are most critical to understanding where, when, and why tropical storms intensify. Now, the magic in all of this is the fact that the glider comes up every 4 hours and sends a subset of its data. So it comes to dedicated servers in our lab, and through SECOORA, we provide it to a data assembly center. Same way that buoy data is processed and quality controlled, and then contributed to larger databases. It goes through the National Data Buoy Center and 2 telecommunications gateways. So it's available for assimilation into national and international forecasts. So the US Navy Global Ocean Forecast System picks up these data and uses it in the form of data assimilation to move the solutions of the ocean forecast closer to the observations that have, in many cases, been collected just hours beforehand. Similarly, the NOAA National Global Real-Time Ocean Forecast System uses these same data, which goes in to feed the NOAA regional coupled hurricane models. And that's the product that goes to weather forecasting offices and to emergency managers. So in this process, in the regional and at the national level, we collect the data. The data go into ocean and weather and ocean models. Groups of us in this community analyze the data and the models, and in a small group of regional leads, we provide weekly briefings to the NOAA Environmental Modeling Center, and through other projects, provide some storm response communication with the National Hurricane Center so that we can see our data and how well our essential ocean features are represented to better assess the performance of the models. And all of this goes into forecasts that are issued to communities. Um, and some breaking news this week that we're very, very proud of. This started off as a volunteer project in 2018. Let's see if we can make the data trustworthy and certified and get them through the pipeline. And that was in 2018 when we did a demonstration project. And as of this week, gliders are officially an operational part of the National Hurricanes Operations Plan, which is a huge, huge win for something that started as a volunteer academic project in partnership with NOAA to make it into the operations plan. So in our area, what are the essential ocean features we care about? You know, the big baddie in this plot here of sea surface temperature is the Gulf Stream, which represents a lot of heat and a lot of tropical cyclone heat potential, but it also provides a basin scale influence on the oceanography of the entire Southeast Atlantic. It also contains strong temporal and spatial gradients that are really difficult to represent in models. So by sending our gliders to the areas that have the highest errors, we can hope to correct some of those errors in the ocean model and how they're tied into hurricane forecasts. Secondly, shelf stratification, so the temperature and salinity that are incorporated into these models through climatology is generally old and cold, as they say. So it's older, colder, and saltier than what we see with our observations collected with modern methods like gliders. And I'll point out that like we put these gliders into storms, but it's important to have observations before the storm so that you can precondition the models with actual conditions during the storms and after the storms to assess the storm passage. The same features that make it really important to work in our area also make it really hard to work in our area. The strong currents and strong gradients that make it so important also make for really active piloting. When you're flying gliders that only move at 25 centimeters a second through currents that are 10 times that speed, these features are not represented well in models, and so you're kind of flying blind. You're trying to correct the errors. You're flying through the errors that you're trying to correct. And satellite coverage doesn't always provide a lot of help either, because the Gulf Stream often generates some of its own weather. Clouds make satellite coverage in our area really poor. In a recent inventory I did for another analysis, I found just 25 decent satellite sea surface temperature images from a period ranging from July till November 2021. So we really are flying blind in some areas. By the numbers, since that demo season in 2018, we have flown 58 glider missions with nearly 2,000 glider days in the water, with an estimated more than 600,000 temperature and salinity profiles collected during hurricane season. This came in the form of missions supported by SECOORA, through the observatory and through external and supplemental funds. Those are represented in the cyan lines. And then we have a partnership through IUs and the US Navy, where they provide our gliders to us, and academic partners provide guidance on where, when, and how to to put these instruments into the most important places. We've focused that on the far side of the Gulf Stream, and we've also coordinated with uncrewed surface vehicles at the surface. We've attracted over $1.7 million in supplemental funding since 2020. And as part of a national impact, we've contributed glider intercepts. We've had named storms with gliders in the forecast cone, and major hurricanes with gliders in the forecast cone. Some highlights here are from some of the storms you've seen. We've had gliders in areas where features are not captured by models. We had gliders on both sides of Idalia, coordinating with autonomous surface vehicles, and the same for Hurricane Milton. And in both cases, these were storms that tend to regain strength in warm waters of the South Atlantic Bight. This is just part of a much larger hurricane observing system that includes gliders, planes, hurricane hunters, floats, and drifters, coordinating it all together. I'm going to scoot through this super quickly so I can get to the fun stuff with outreach. It's almost unfair to work with yellow robots and hurricanes, because for the first time in my life as an ocean physicist, people care about this kind of work. So they're very easy for outreach. And we've gotten a lot of wonderful press who joined us on glider deployments, and expanding the impact of this work. And really how important the ocean is for our weather on land. And this goes beyond hurricanes. You can think about bomb cyclones and winter storms, sting jets and other weather systems, even the sea breeze that guides our day-to-day here on the coast. So gliders are an everyday kind of a thing, but particularly powerful during hurricane season. Thank you so much.
Great. Thank you so much, Catherine. And huge congratulations for the many years of the deployments, for showcasing how valuable gliders are for forecasting, and for the Interagency Council for Advancing Meteorological Services for integrating the ocean glider data into their 2026 National Hurricane Operations Plan. I'm going to go ahead and ask you to stop sharing your screen and bring the speakers back on camera for some questions that have come in. And so one question we've had that's come in is, we've talked about these components, WebCOOS, buoys, and gliders separately, and they're curious, how does bringing them together into an integrated observing system improve hurricane preparedness and response? And Debra, that might be directed towards you.
Well, I know my fellow panelists can answer this question as well. I mean, each sensor provides a different stream of data, and not all of them are in the same place. It'd be super amazing if we could co-locate cameras and gliders and buoys, but they're all spread out in different places. And you look at a map with all these assets and big dots, it looks like we've covered the geography really well, but the fact is there are still huge gaps. The beauty of bringing it together, though, is you can sort of validate and what you're getting from different sensor streams. And models are not modeling just wind; they're modeling a combination of parameters. So having multiple sensors out just really helps improve the overall forecast. And then I'll just hand it to, I don't know, Catherine or Greg or Lynn, if any of y'all want to correct me, because I don't have a PhD.
Well, the one thing I was just going to also add to what you said, Deborah, and I'm sorry if I jumped in. So, but I think that as a buoy operator and having the other types of measurements, I mean, Catherine's covering a lot of distance, right? We're sitting in one place, so I'm sampling intensely at one location. Her assets are getting that spatial coverage. And when you are operating, at least from my perspective, the buoys, and we're very concerned about the quality assured data, I think having sort of that spatial representation of the data to evaluate the performance of the buoys that are only looking at one place can be really important. So I think in addition to the modeling that you mentioned, Deborah, I think also that we use, at least I use other people's data operationally to kind of make sure that the observations we're providing are as quality assured as they can be.
And I'll add on to that and say that, it's not just providing the observations and putting them on a website somewhere that hopefully somebody knows how to get to and can come back to when stuff's a coming. A lot of it is that ongoing conversation where the data providers are looking at what's going on and making comparisons to models and saying, oh, that's something's hinky there, or having those relationships with the forecasters to be able to bring it to their attention, to say, hey, look, there's a feature that's not well represented in the latest flavor of the model, and you may want to take a closer look. That's a huge part of this that goes well beyond just the data product.
Thanks all. And Greg, this question is directly from you from the chat. Do you think there might be challenges or for the RIP current project? Do you think there might be challenges because the identification is done based on polygons, especially considering not all cameras will be facing directly to the beach?
Yeah, that's a great question. Yes, there are challenges. I would say it's not necessarily polygon related, although the camera orientation and angle is a big part of it. So one of the challenges we've seen is that, when we developed the model, it was using a wide range of imagery to try to make it generalizable to detect rips. But when you add a new location that the model hasn't seen before, it's probably not going to work well, both because of potentially the orientation of the camera, but also rips look a little bit different in different places. And so the detection model is definitely sensitive to new data. And, I think what we've seen with some of the experimental tests is that we really need to add new data from those sites to retrain the model to make sure it works well there. I would just add there is an alternative approach we developed to detect rips using optical flow. So instead of doing kind of box-based detection, actually tracking the flow of the surface of the water and then using AI to note where that flow is anomalous. And in that way, we're able to detect rips on a pixel by pixel basis instead of a polygon basis. And it works really well. The problem is it's really expensive to run computationally. And so I know the team's been trying to come up with a way to do some testing operationally with that method, but still in the works. So great question.
Thanks, Greg. Another question has come in from the chat. Is SECOORA utilizing high frequency radar in preparing for hurricane season? If so, how? If not, why not?
So great question. I'll start and then maybe ask Catherine to add on. The radar data when the stations are operational is always available. And what it provides is near real-time surface currents, which can be dramatically impacted by approaching storms. And so being able to see the radar data can help, again, verify forecast and provide some insight into what's happening with surface currents and a bit about the wave environment as well. I'm going to kick it to Catherine and see if you want to elaborate at all.
Sure, yeah. I think there's some other features that HF radar systems can also potentially provide. Dr. Stephen Lazarus at Florida Institute of Technology and I have been talking about how to, in some of our systems, we can use the HF radar returns to invert to see what the wave field is like. And so our partners at Kennedy Space Center, where I have a radar system installed, is really, really, really interested in the potential for that kind of product. They're very interested in corrosion on their systems, on processes that affect beach erosion, and then corrosion of their built systems on land. So that's something that I think Dr. Lazarus and I are really interested in exploring in the future. And one example of how you can potentially use not just the direct products, but derived products as sort of at this point, it would be highly experimental, but it's being used in other places, and it could have significant value for stakeholders.
Amazing.
I'll just add that for right now, quickly, sorry, Abby, the the surface current data set is extremely dense. So it's very challenging to pull into forecasting models. So it's it is used by the Coast Guard, but is often more situational awareness sort of data set that those that are aware and familiar with it use. Thanks.
Great, thanks. And seeing the time that we only have 1 minute left, I'm going to read some comments from the chat. Mark Fisher, as an active Coast Guard watchstander, uses current buoy data on a regular basis. This data guides station rescue teams with critical insight when executing search and rescue protocol. So this data is used just beyond hurricanes. So thank you, Mark. And then also we have Kristen Becker from the Florida Department of Environmental Protection. She wants to extend kudos and appreciation for all the work that we do. They use the various data in the Office of Resilience and Coastal Protection. So we really appreciate you guys joining the call to learn more about our observing systems. And this webinar is recorded and we'll share it with everyone registered. And I want to give a special thanks to Catherine, Lynn, Greg, and Debra for joining us today. Really appreciate it. And I hope everybody enjoys the rest of their Wednesday and has a great lunch break.
Thanks.
Thanks, everybody.
Thank
Thank
you.
you.
Bye.